The final topic I wanted to cover was kind of moving. So we kind of moved to data centers, and I wanted to cover on how sort of building power management gets done, and that's something which sort of came along in some of the earlier lectures, but it's sort of a culmination of from computing, then data center, and then towards the buildings. Okay, so this is a topic which has received a lot of attention, and in fact, there's a major ACM conference which started in recent years called ACM Buildsys, and in general, energy of buildings, built environment, cities, this is kind of a topic which is receiving a lot of attention because of essentially obvious reasons. Even things like transportation and all, it turns out energy is a significant consideration. I've shown this plot very early in the course, which is how because of these reasons, there is a fair bit of detailed accounting. So there is a US agency which kind of really keeps track of every joule coming in and out, conceptually at least, where what happens. And one of the particular focus really has been on buildings, mostly because buildings consume a fair bit of energy in various forms, and also indirectly as well. Interestingly, one of the largest consumers of energy in California is actually the water that we use, and part of it simply is because water gets shipped and heated and drawn from the ground and all, and it's true in many other parts also. So many different reasons why buildings either directly or indirectly end up consuming energy, and it's growing. Okay, so it's kind of look at the trends and all. I guess there's a lot more intense uses of energy. When I look at my own home and all, which is or basically had to upgrade the panel because good old days when the electric panels used to be just 100 amp and all, they're insufficient for a modern household. Nowadays, it's very common with people with electric vehicles and all. Again, they're putting increasing the electricity consumption. Some of it is energy being shifted. Net energy footprint of a building, which is what sort of essentially was one of interest, is the load minus the stuff which is locally harvested. So you can think of it as you could define, just like for data center we saw last time, PUE, power usage efficiency. Similar thing you can imagine for a building, that for building to do its task, there is certain net energy usage which is kind of needed. And by and large, this is very little. So for example, if you go to the student center out here, they actually have a big solar panel. But if you look at the total usage of the student union versus what the solar panel provides, it's like a few percentage points, very tiny. So we are still quite far off from, at least in normal buildings, from making this thing to be a very significant component. But on the other hand, there are people who are deploying kind of entire roofs which are solar panels and all, and they typically give you 3-4 kilowatt type power at its peak, and they for many it begins to provide some significant amount. So what my goal was to show what kind of information technology, particularly sensing, but also increasingly control, are being brought to bear to manage and understand this load. And in fact, at UCLA, there are several faculty, Bill Kaiser's group, for example, or Jeff Burke, or Margaret Delmas. There are several faculty, Rajat Gad in mechanical engineering. A lot of people are working on problems around this. So the holy grail is, could we have net zero energy buildings, or actually also net zero enterprise or net zero campus? UC Davis and UC San Diego, for example, have been putting in a lot of efforts in that direction. They advertise quite a bit that how their total intake from the grid minus total output back to the grid, because they locally generate, essentially adds up to zero. So goal basically is, through clever management and all, could we basically achieve no net footprint. And there are a couple of things that sort of both of which are needed. One is local generation, but local generation is never going to add up. So the other part is managing the energy, reducing the load. When it comes to reducing the load, there are basically two ways to go around doing it. One is to have intrinsically lower energy consuming appliances or things like computers being lower energy or lower energy lights and all. But the other part is modifying people's behavior so that we either shift the load, the energy usage to times when it's more preferable, or even reduce the energy usage. So a lot of initial work in information technology, really applications in this context, really has been in this latter category. That how can we reduce it? I'm going to skip this slide. So where does the energy go? Again, just like for computers, when we spent some time trying to understand where computers consume energy, same kind of analysis for buildings also. There are some surprising things. There are a lot of things that you would think that, like one article I was reading was, people overestimate how much energy they use for lighting, and they underestimate how much energy they use for things like HVAC and cooling and all. So lights are an obvious in-your-face thing. So if it seems like we left the light on in a room and all, we kind of overestimate its implication. Whereas on the other hand, 1 degree Celsius change in your HVAC setting at home has a much bigger implication. So a lot of work has gone towards trying to really quantify where the energy goes. And unlike computer, where you can hook up a power meter and be done with it, buildings are obviously a lot more complicated in trying to understand these things. So first thing is just the type of energy consumption. Turns out, at least in the US, electricity dominates, but that doesn't have to be every place. The other thing is, certainly, unlike computers, buildings change over a much longer time duration. Average building has a lifespan of several decades, if not more. Population density matters, and then there are climatic differences. Obviously, building in LA versus a building in Boston would behave very differently because of just the environment, just the climate conditions that we face. And then, of course, age of the building, maintenance, and all. So just in terms of, like, if you look across things, New York City is actually supremely efficient simply because people are packed into a smaller, much more efficient usage of building. On the other hand, Houston, Phoenix, sort of cooling requirements. So you basically end up seeing some of those effects as well. In general, I guess moderate climates are going to have better effects. So that's sort of obvious. And usage breakdown. So this depends quite a bit on type of building you are looking at. So, like, for example, this is on the right-hand side, we have what is for home or residential building. And you see that if we look at total energy use, so electricity plus others, heating or cooling, HVAC, those kind of things take a lot of time, whereas a lot of other stuff basically are little, they kind of add up, but bulk is really cooling and heating of water and space. When you go to commercial buildings, the mix begins to change, but sort of similar type of, again, HVAC and these kind of things end up dominating quite a bit. If you look at electricity alone, again, big office buildings, all commercial buildings, and you begin to see that within electricity, lighting dominates because cooling and heating are usually done sometimes by electricity, but by and large, they get done by natural gas or oil or some different form of energy. And one factor which I referred to earlier also is the office equipment component. This is sort of growing quite a bit. I've shown some studies out of Berkeley and UC San Diego where, at least in some kind of buildings, that has begun to be a pretty dominating thing. So what's happening is that some loads are naturally decreasing, like interior lighting, as we move. So, for example, tungsten lighting is now, by law, I guess, cannot be sold. So over the next few years, we'll gradually see a decline on the lighting side, LED and compact fluorescent. On the other hand, office and computing equipment is penetrating more and more. So the balance certainly is kind of changing. Natural gas is the other form of energy use, and that dominantly goes into sort of heating or heating water, heating a lot of in California in particular, a lot of air conditioners also operate on natural gas, so that's sort of the normal thing. Time of day and month of the year, these things also play a significant role. So the load is not static, and that matters because um, electricity generation or energy generation is um, not constant. So particularly with renewables and all. So what this is showing is that weekend versus weekday, and you might imagine that June versus December, these are all going to have different characteristics. And the problem this creates is, so just like we saw in data center, over provisioning costs a lot. That is, if you design a system which is designed for the peak, then there is a baseline cost you are going to play in terms of your energy infrastructure, and that's going to sort of increase kind of the baseline power. So the strategy is somehow you want to also have a system which is provisioned for a lower point and then shift the demand, as opposed to leaving the demand untouched and then designing an energy system, generation and distribution system which is aiming for meeting the peak, because then at all times you are going to pay the cost of that baseline. So designing in California, to translate into designing for electricity system for the mid-June air conditioning load during the hot part of the day is probably not a wise thing to do for the rest of the year. So you want to somehow therefore encourage that load be shifted. So what kind of things do you think are being done for shifting the load? These kind of things get discussed in news and all. So what kind of strategies do you think are being done? So essentially kind of the theory is that if I can avoid building a power plant, that is better than building a power plant and building things. So Jeremy.
Putting a battery in the house.
Okay, so putting a battery in the house can shift the load because I can charge the battery at times when, and I'm sure in, I guess just a week or two ago, Tesla had this big announcement that their new business is creating these lithium-ion battery packs, which they're going to be selling for a few $1,000s at home for this particular purpose. So battery pack, or do you think there are other ways we can store energy? Store and recover it. So battery is one, but other thoughts? So one strategy which some countries and actually even is basically gravity, namely pump up water and then store the energy there, and then when the actual electricity is needed, you kind of bring it down and have the generation being done. So essentially you are shifting generation capability based upon that. A similar concept is being done for thermal related stuff. You heat things and then use the heat at a later point in time. So these are all essentially kind of batteries that are natural batteries that are occurring. So shifting load by actually storing energy and using it at different times as well. What else do you think can be done? Is there a different strategy as opposed to kind of storing energy?
Change usage better, maybe.
Change usage by?
Using usage better. For example, if I'm doing my laundry at the evening, I should better do it in the morning.
So what will make you do that?
An incentive.
An incentive.
Either
an incentive, a bribe or an order, right? One or two. So, so what form this incentive can take?
Lower prices.
Lower prices. Okay. So one strategy which has emerged is that they say, okay, we're going to give you a lower electricity rate, but your air conditioner or some other big appliances, the switch in front of them is no longer under your control totally. It has a radio device and the electric company can shut it down. So this is common in many parts of the country where essentially in return for a lower price, you are basically saying they can shut it off. Okay. So that's one. Another strategy is something called automatic demand response, or just simply demand response. And the concept there is that the price of the electricity changes, and you somehow have a display. So at home you will have a display, what's the electricity price, and the idea is that hopefully you would modulate your behavior based upon that. Okay, so there are a couple of ways. One is manual, which is they're displaying this thing, and you are seeing that okay, you're paying more for energy and kind of just relying on the human reaction. So that's one strategy. The other strategy is that again you hand it over. So automatic demand response means that there is some unit at your home which would then look at the loads and all, dim the lights based upon some policy that you would have specified, or in a building like this, maybe loads can be classified into, prioritized into different levels, and then some of them will be shut down and all based upon some policy. So like maybe critical equipment will be kept up, but the rest are brought down and all. So a lot of strategies can be imagined. Now, the nature of the loads, has this again was a slide I presented at the very first lecture, which is nature of the load is changing. So computing loads and all are becoming, or kind of just generally smarter appliances are becoming a big part of both office buildings and homes and stuff like that. Fortunately, these also tend to be the one which perhaps can, whose load can be shifted quite a bit. Modern buildings are kind of often being dominated by this. So this concept of power proportionality, which we saw in computing, which is that most of the time things are, we design them for some peak operating point, but then most of the time we don't use them at peak operating point, but then we pay for that inefficiency throughout. Same thing actually holds true for buildings also. So this is Corey Hall is the EE department building at Berkeley, and what you see out here is that a significant kind of variation that you see, and this is actually across the entire UC Berkeley campus. And what you see out here is sort of the big range that exists across the buildings in terms of their kilowatt hour per square foot versus kilowatt hour. So sort of the average versus sort of the intensity, and some of this is reflecting the nature nature of the buildings. On this campus, what kind of buildings do you think are going to be more energy intensive? Any ideas, thoughts, like what are the big energy consuming stuff? Why? No, but energy intensity, right? I mean, you have to normalize it to the size of the building, right? Okay, so certainly, so one way of looking at it is size of the building, aggregate power. I guess in that one, Reagan Hospital will probably win handedly, okay? But then you also have the intensity part, which basically means the type of work you're doing. So office rooms like these or classrooms like these are relatively low intensity, okay? On the other hand, wet labs where they have fume hoods and stuff like that, those are big power hungry kind of things. So that, or like the nano lab in the bottom floor of E4 or the similar one in CNSI, these things are far more energy intensive that way. So buildings tend not to be very energy proportional currently. I mean, the baseline power consumption is sort of pretty tremendous. So they kind of act like computers in their energy proportionality behavior. This is, I think again, Stanley Hall. I don't know where it is. It's either Berkeley or UC San Diego. You see kind of in this particular case, there is more variation, even more variation. So this is basically saying min versus max ratio, which is kind of giving you a sense of how energy proportional building is. Now, clearly, a lot of these buildings are not being used much. So ideally, you would expect that energy proportional building during times when it's not occupied would really go down. But what ends up happening is some of the loads like cooling and heating, these kind of loads, they are essentially on all the time. They occupy a fair bit of energy consumption throughout. So some of the interesting ideas that people have been exploring in recent times are, if you think about the air in a building, it's actually again a form of energy storage. So classically, when it comes to HVAC, the way these modern buildings, the way the current buildings like Bolter Hall and all are managed is the following. Somewhere in the facilities, they kind of decide that based upon some gut feeling and all, they decide that, okay, classes start at 8 a.m., people leave by 5 or 6 p.m., we are going to set the HVAC so that it kicks on at some time of the day, goes off some time of the day, and these are kind of policy, and then they may have a different policy for weekend, and they'll kind of leave it at that. Problem with that is not every day is the same, things change, so the next smarter type of thing is maybe begin to make use of occupancy somehow. Actual occupancy behavior. And then going further, concepts which have begun to emerge now is preheating, pre-cooling. So the idea being that we actually begin to make use of some predictive analytics, prediction about occupancy in order to begin to heat and cool right time, because essentially we have a big time constant involved in these things, and that you can begin to exploit. So buildings exhibit sort of this one is actually kind of a nice building, as you can see, a lot of variation which is happening. So it's clearly making similar stuff at other places as well. So main observations: energy consumption is diverse in buildings. HVAC and lighting tend to be kind of the big consumers, but IT plug loads, namely IT equipment, is emerging a big one. And then finally, they are actually rather energy non-proportional. There is another concern in many settings, which is this notion of water embedded energy, or kind of this is representative of indirect uses of energy. So let me ask you the following question. So as I mentioned earlier, when you use water, you use energy indirectly, right? Water is drawn from the ground or whatever, it's transported, it's cleaned, it is heated potentially, and things like that. Okay, so the potable water or drinking quality water that you get has a fair bit of energy. How much energy do you think there is? So let's say I leave a faucet running for 5 minutes. How much energy do you think am I consuming? What do you think would your gut feeling be? Or let's rephrase the question. Let's say I have a light bulb, 60 watt light bulb on for some time t, and I have water running on a typical faucet in the US, typical faucet running for, again, some time t prime. What do you think is the ratio?
I would think the water would use around maybe a little more than the 60 watt light bulb.
Water would consume a little more than 60 watt light bulb, right? And in this case, I'm really talking about all the energy that went into creating that water, whatever, right? Yeah, because turns out that 5 minutes of water usage is roughly 14 hours of a light bulb on. So pretty dramatic ratio, and we kind of obviously never realize this. The point is that there's sort of all these indirect vectors of energy usage that that occur, and in many settings, this is becoming a big issue. We in the state, we are going through a water crisis. We are sitting next to Pacific Ocean, so obviously lots and lots of water. Why don't you think we do desalination? Takes way too much energy. Way too much energy. The only parts of the world where desalination is being done is where either there is total desperation, Israel, or energy is plenty, like some Middle Eastern countries. Okay, so or another alternative, which is what is called as brackish water, which is essentially water which is dirty. You kind of re-clean it and bring it up. Again, these processes are energy hungry. So there is certainly this kind of indirect usage of energy which is wasted. Another one, I'm sure you have encountered hot water faucets, which you turn on and you need hot water, but the water is cold in the segment between the heater and your faucet. So you leave it running for a few minutes. Not only is the water being wasted, but also that segment of the pipe which was heated. So there are a lot of these in the water system. There are a lot of these systematic places where energy is used and wasted, and also buildings use plenty of amount of water, and by the time you kind of so firstly, right up front, energy usage fair bit goes into heating water, but that is just a direct use, a visible use. But then energy is also used in all these other processes, which is to create water, which we are able to use. So roughly 3-4% of the energy usage goes into creating the water, but this is worldwide. If you look in California, 20% of electricity is for water usage, and in most cities, the single most direct use of electricity, is actually the water company. In some other places, it can be even more dramatic. So, like from India, some data point there, which is in agricultural states, got 30% goes into, because they pump water, and the same thing is kind of happening in California, that pumping water out of the ground, and that takes energy also. This was the stuff which I mentioned. Faucet for 5 minutes is 14 hours of a light bulb being on, so quite dramatic. So that was yeah. So this is a typical water use cycle. Lots of places where energy gets used. The other thing is that these intensities differ quite a bit. So the same unit of water is roughly 4 times more energy intense in Southern California, because we get our water from far away than in Northern California. And so this is commonly referred to as the water energy nexus. The fact that energy is required to use to create water, and energy is required to make water, and water is required to make energy, and there's kind of a vicious circle that ends up happening out there. So let's now go to how does information technology kind of help in this thing. So I guess the interest in this space started maybe roughly 10 years ago or so, when sensing technology advanced to a level where people said, look, we can begin to use these things to do some energy-related improvements in buildings. And one of the early things was making building energy use transparent. So kind of the idea is that one of the ways perhaps we could motivate people to use less energy is to actually give them an insight into how much energy they are using. And there were some studies which showed that that might be beneficial. So for example, there is an effect called Prius Effect, Prius being the car, the Toyota car. And the effect is, so I don't know if any of you have seen, but in Prius what happens is there is a constant display of energy use that is happening, and the effect is that people drive more energy consciously. Okay, and in fact, for some of the hybrid cars and all, if you sort of there are people compete that how long they can go without refueling the car, and refueling as in with gasoline and all. So it's kind of sense is that by making visible how much resource you are consuming, perhaps you can do better things. Some other studies also indicated, like for example, in dormitories where students do not pay for energy use just for their building, or other multi-tenant homes where people do not pay for, they do not have a meter just for their apartment, but they just get charged indirectly, people tend to be more wasteful of energy. On the other hand, places where you're actually metered, they tend to behave better. So making building building energy use more transparent, how much is going where is kind of the main concept. Okay, could we begin to decompose things? So there's a fair bit of work happening in this space in some pilot projects like this. Again, so sort of UC Berkeley has been doing quite a bit of deployments like these, where they really sort of making use of sensing technologies and all, begin to kind of decompose instead of just getting a sense of how much the whole building is consuming. You begin to decompose things like that. Look at our own buildings out here. Many of our labs are very energy intense, but we are not metered individually. Okay, so we are metered in a very indirect fashion. The way it works in most organizations is they charge a certain percentage of like the grants I get. Roughly a third of it goes to the university, which is indirectly used for all these things like energy that I use and all. And once I pay that, I really have no motivation to save energy, okay, because like it's going to some central pool and the effect is very indirect. So kind of the model is shifting towards that if we kind of begin to make specific uses more visible, perhaps we can do better. So so several other uses also. So one is if we know what subsystem level energy is being consumed, then perhaps we can identify things which are particularly inefficient and replace them and all. Another one is that if we again have a detailed view of energy consumption of a building, we can identify faults that are occurring in all, something which is left on, does not go off at the right time, things like that, or just general degradation. You can use it to control loads more effectively. So as I was talking about HVAC, smarter control of HVACs, for example. And then finally, to modify behavior, this kind of an indirect effect that by shaming people and all, one could do it. So an example of this one, so over the past few years, Professor Bill Kaiser and Margli Delmas, these guys have been running the study in married student housing and the dorms out here. What they do is they instrument the dorm rooms and all with these sensors, and then they take that data, and it's not being built, but what they do is they display it as a public board. Okay, so like which wing of the dorm is more green, or which room was greener, or kind of do various kind of studies in terms of seeking to influence the people's behavior. So these kind of competitive strategies are, for example, one of the things that one could be enabled.
Is that in the dorms here?
Yeah, it's in the dorms here. Couple of the dorms, not every dorm. Yeah, okay. A few hundred rooms in couple of the dorms.
Okay.
Yeah. And likewise, I think the most recent study was some 100 apartments and married student housing. So again, what they do is they, at the appliance level, they kind of instrument stuff and all, and then sort of provide this data. And there are many. I'm citing the UCLA study because it took place here, but there's similar studies at other places that have happened. And some of the newer campuses like UC Merced, for example, or also UC San Diego, these guys have instrumented buildings, and also like faculty gets like each office is being essentially kind of metered and all, and again kind of seeking effects. So transparency potentially kind of is useful. So kind of the idea is that it can, this kind of a fine-grained observation can sort of provide things, provide deeper insight. More generally, kind of what research and systems of this nature are doing is that, look, buildings, if we were to put a sensing infrastructure, not just measuring energy, but other contextual aspects also, occupancy, ambient conditions, things like that, then we can make a variety of different kind of inferences from it, which can then be used, roughly speaking, for two purposes: automatic control of building systems and seeking to affect the occupant behavior. Going back to like take the automated control. So for example, when I mentioned earlier, the automated demand response. So currently what happens is a signal comes from the utility company which says reduce your energy. And then, like I said, there are some static policies which kick in, and they'll say, okay, these rooms are going to remain on, these rooms are lower priority, we're going to shut them off, or maybe things like lighting can be reduced, but maybe we'll not do it for the computing equipment and all. If you have a better insight into what is happening, then perhaps that load shedding could be done in a smarter fashion. So these are kind of things that people are exploring quite a bit. So starting from a number of years ago, you see kind of the very early papers, 1985 and all, people in behavioral science, they've been exploring this facet quite a bit, which is, does insight affect energy consumption? And the UCLA project I was referring, which is actually still ongoing, it started a few years ago. That's the one in dorm and managed student housing. There are, roughly speaking, the findings are advantages. Self-monitoring or making things visible are useful, but the feedback needs to be actionable. So what I mean by that is, if you simply show me a graph of my energy consumption, it's probably not going to be terribly useful. On the other hand, if you say a 1%, a 1 degree Celsius reduction in your thermostat setting is going to save you so many dollars, that's kind of actionable information. It needs to be high frequency in the sense that if it happens once in a while, every year you send me a reminder saying, okay, if you were to be more conscious about turning off the light, you'll save energy, you'll probably get ignored. So it has to be continuous or sustained. It should be high frequency. Possible benefits. Now this is where kind of the data is kind of interesting. So some studies have shown that there are significant reduction opportunities, 20, 30, 40%. And kind of nice thing is that they're essentially coming for free in the sense, just by providing information, you don't have to change stuff. But there have also been studies which have shown that there is actually an increase in energy consumption. Why do you think that might be? So after information is provided in these kind of settings as to how much people are consuming, actually the energy consumption went up. Why do you think that might happen? And these are just behavioral questions, nothing to do with
They anticipated it's going to go down, so
Huh?
they anticipated it's going to go down the consumption, so they use,
Well, okay. Or the other thing is, hey, I'm actually below the average, and therefore I'm going to consume more. So some studies have found that the effect is actually goes up, interestingly. But by and large, most studies, the UCLA study, I think the number was that like the HVAC consumption went down by like 30% or something like that. So there seems like there's some interesting potential benefits out there. There are other evidences from old studies when the fine-grained part was not there, but what they compared was apartment buildings where there were meters for individual apartments versus not, and what kind of otherwise identical buildings, what kind of differences were there. So the general thesis is that it's beneficial to give a finer grained visibility into energy consumption. Okay, and I guess the analogy I will draw is on the computing side. Is it beneficial to have subsystem level energy consumption data, as in how much is the display consuming, how much is the memory consuming, how much is the processor consuming, and could the applications make use of that? Thesis out here is that fine-grained from two aspects. One is how much different subsystems of a building are consuming, and the other is how much different individuals are consuming. Okay, both these kind of decomposition potentially are useful. So this field of study, the term which is used in literature often is called disaggregation. That is, I take this overall data consumption, and I disaggregate it. Now, fundamentally, this is a problem of measurement. Okay, how can I sense and decompose? So if you think about it, traditionally, the kind of stuff that we have been good at modeling is really kind of at a very coarse level. I can do like coarse and low frequency. So traditionally it had been just your monthly bill or bi-monthly bill that would come in. Then we kind of migrated towards where we have now smart meters and all, and depending upon your service provider and all, you may have relatively immediate access to it. So like for example, now at least at my home, Southern California Edison, which supply, not Southern California Edison, gas company. So they basically have put a smart gas meter, and essentially at the end of every hour, I get to see how much I consumed at that hour. So they have an hourly update, and I think this is a citywide deployment that has happened. In many places, you can have immediate access to your electric data and all. In other cases, you can have less frequent, but still higher frequency access. So that's one. Then finally, you could begin to go, but this is still whole building, okay? Then what has begun to happen is that essentially endpoint level decomposition. So in some places, now when you get your electricity bill, they decompose it. So they say, this is your overall consumption, but by the way, your refrigerator consumes so much, your oven consumes so much, your pool motor consumes so much. So there are a couple of ways you can imagine doing something like this. One is along the lines of the paper that actually Fatima had presented last time, which is if I have multiple principles, how can I decompose it? Okay, so I'm measuring the overall power consumption, but then somehow have to decompose it just from that data. So with the rise of machine learning, analytics kind of stuff, what has begun to happen is there's a company called O-Power, which got a lot of splash. What they do is they work with utility companies and they take your smart meter trace. So the smart meter traces are high frequency, but not something that you get to see, but they're sort of going to this company and they do pattern recognition on it. Okay, so they kind of identify, okay, this pattern looks like the refrigerator one, and they decompose and give you kind of an estimated sort of data point. So utilities are interested in it because kind of some of the legal requirements which have come into play, but there's a lot you can do just from the smart meter data. And then there are technologies which basically are creating a variety of sensors which are at the outlet level. So these are some of the older pictures, but like just this year when I look at products, so there's like a local company called Belkin, I'm sure some of you may have heard of it. They make a lot of these smart devices, peripherals and all. One of the product line is called Wemo, and which works with this IFTTT, this, that. So these are smart little outlets and all, but now you have the ability that your wall outlet, by the way, also measures the energy and which can be queried, okay? And there are many such products at this stage at sort of different granularities and all. They are expensive, $50, $40, somewhere in that range, but endpoint level stuff that you can begin to do. And there's a lot of research going on essentially making that kind of technology cheaper and kind of lower finer granularity and more accurate and all. So the key thing out here is really being able to disaggregate. Okay, so I'm giving you some sort of a trace of energy and I want to decompose that. So one way is this signature analysis. The other way is put sensor every place. So if I want to disambiguate between these things, I could adopt these strategies. So first approach, kind of the obvious one, is this direct sensing, which is wherever I need to know the energy consumption, I actually put a sensor. So this would be the counterpart of that. If I want to know energy consumption of different subsystems in a computer, I put a current sensor at each one of them. And indeed, there are just like there are computers which provide these kind of sensors at a subsystem level. There are you can do the same thing at a building scale, for example. Obviously, the reason not to do this is cost, because I just mentioned that each one of these sensors currently are $40, $50 if they are plug level, and if you have to do some call an electrician and all, then it would be even costlier. But you could do that. And one group which works quite a bit in the space is University of Washington. So that was a slide from them. Okay, so so that's sort of direct metering kind of an approach. Okay, so very commonly these sensors take the form of either they are inline, which is you put them, you install them, either you replace the outlet or you put something on the outlet and then your appliance kind of plugs into this. Or the other way they work is wraparound, which is you take a electrical cable and your sensor goes around it. So very briefly, current sensors, how can you sense current being consumed by something? What physical effects can you use? Or let me rephrase, how much, your task is to measure power being consumed by the appliance. So what are the different ways you think you can do it? What physical effects you might use?
With voltage?
Hmm?
Give it constant voltage and measure the instantaneous current change.
Okay, so I need to know voltage and current, okay, to get the power. How would you measure voltage and current? So fundamentally, we know how to measure voltage across something using a multimeter kind of device. Current sensing, well, how do you sense current? Resistor convert current to voltage, right? So essentially, I measure the voltage to ground and I measure the voltage across a very low, high precision resistance, and this is the kind of stuff that you guys are using, and I kind of measure stuff. Okay, and I multiply voltage by current, I get the power, and I kind of do an integration over time for that. Okay, can you think of some other way of measuring current? So the problem with this approach that I just described is you need to have a resistance in series, right? And if you are talking about this kind of stuff, that resistance is going to be carrying potentially, our outlets are 15 amp, a lot of current going through them. So can you think of some other way of measuring current?
There are ways of using the magnetic field.
Yeah, so going back to our physics, magnetic and electric fields are related. Change in one causes change in magnetic field causes electric field and vice versa. So that effect you can begin to use. So essentially, when the current flows, particularly AC current, which is a sine wave, then there is basically a pickup that you can done of the field nearby. So you could have, so instead of inline, which carries sort of issues of the actual current is flowing through it, you can basically have a current sensor around the wire. But the thing is, you have to have it around the wire, so you cannot simply have it around the whole cable because then the current in the two directions is going to cancel out. So if it has to be along, let's say, the hot wire. Okay, so so this kind of several different types of these things kind of exist. The main point is I need as many sensors as the number of loads, very high accuracy. You can measure voltage and current and power as a function of time, so it gives you a very precise data. Then the second class of techniques which have received a lot of attention, and there are actually entire conferences based around it currently, or a few workshops and conferences around this, and they basically rely on estimation, machine learning kind of techniques. Kind of the basic idea is the following. If you look at power consumption trace from some home, what you would see are signatures which are very correspond, very unique signatures which correspond to different kind of appliances. And also in this particular case, what you are seeing is that there is a refrigerator which is kicking in at some frequency, so compressor comes on and off, but then there was also at some time some heater kicked in, and the heater's energy consumption is sort of additive, so it kind of adds on top of that of the top of the refrigerator. So looking at this, you might say, through some smart algorithm, clearly these things seem separable. Okay, there are kind of multiple different unique waveforms which are being superimposed. Perhaps I can separate them out. So this class of techniques are called as non-intrusive load monitoring or non-intrusive appliance load monitoring, where based upon some signature, I'm going to be able to, the hope is to be able to separate things out. So what happens in these systems, therefore, is there is no sensor at the outlet level, but what you do have is that somewhere at a central point, you are looking for signatures. These signatures may exist in any dimension. So this signature could be in the current, but the signature could also be in the voltage. So we think of AC voltage as something that's fixed, but in reality, if you monitor the voltage, I mean, I'm sure you have seen these things like you turn on a motor or like heavy appliance, and then kind of the lights dim a little bit, right? So that's happening because the voltage express is somewhat transient because the loads are non-linear and the currents, wires are lossy. So there are signatures which exist both in current and voltage, and so one could seek to sort of exploit this. So this idea started sort of quite far back from a professor at MIT back in late 80s, early 90s, but in recent years it has undergone some tremendous revival. This is interesting at some level. So in the sense that you can imagine the power electric company can do this thing from the meter data. It doesn't even need to come and install any sensors. So that what I was mentioning earlier, that O Power works with the utility company, they're basically using some technique like this. Of course, part of the problem with something like this is you have to develop the classification algorithm, and it's just sort of a complicated machine learning problem. So this Nylum or Nalum has, like I said, has received a lot of attention, and kind of the classic paper is this Hart's paper back from 1992, the very early work, the Hart's original work, they basically said, imagine a very simple model that think of an appliance as having a power consumption level. So whenever it turns on, the overall at the meter, I'm going to see an increase in power consumption by some delta. When that appliance goes off, I'll see a decrease by some delta. And the height, that delta, is unique to the appliance. And by matching pairs of upgoing edges with downgoing edges, I can begin to find out when an appliance was kind of active. So they were looking at what is called as a real power graph, that is, you're looking at the actual power consumption, look at the transitions, and then cluster transitions according to those that corresponded to similar level of power changes, and then sort of that gave you time, start time, end time of different appliances. There are lots. The reason the problem is complicated is because this simple model fails very easily. So if I sort of, so one setting it fails is that many appliances, you do not have a particular transition level which is sort of which is always fixed. So many of our appliances have multiple levels of power consumption. Take a fan, for example, it may have different speeds. So when I turn the fan on, the power consumption increase may depend upon what setting the fan was on. Then there are the other problem which comes up is there are appliances which otherwise may have very similar delta changes. Okay, I may have light bulbs tend to be 60 to 100 watt, or laptops tend to be 60 to 100 watt. So how can I distinguish between them? So actually, how do you think we can distinguish between these? So let's take my example. Laptop, 60 to 100 watt. Light bulb, roughly in similar ranges. These are tungsten light bulbs. So if I were to simply look at their power consumption, they're going step increase in power consumption, they're going to look the same. How can you discriminate among them?
The laptop should have a change in the power consumption much more frequently than the light bulb.
Okay.
Because the processor has it'll step up the speed depending on the task you're doing.
Okay. So one thing is that, okay, it's going to change. Now the problem we have is that what happens in the middle is going to be very, in the sense, these changes are hard to track because they're overlaid on changes that are also otherwise happening. But you're right that there's going to be change in the laptop. Do you think power consumption of a laptop differs in some other aspect?
When it's done charging, it's not consume as much power if it's on the battery.
Okay, let's replace. Okay, you're right, but let's replace my example by a desktop which happens to be 60 to 100 watt. So no battery. But you're right.
Time of usage.
Hmm?
Time of usage. For example, the lights are more likely to be kept on during the day.
Okay, fair enough. Possible, yes. So basically, what you're saying is time of day is an additional factor. Okay. I was looking for some more electrical answer, but sure. What else? What kind of load is a laptop? What kind of load is a light bulb? Okay, those of your E's.
Is the computer a more capacitive load?
So these guys, right? Okay, or in these are. So how do so light bulbs, at least tungsten light bulbs, are basically resistances, right? Whereas these other loads are inductive, or in some cases, these are so-called switching mode power supplies. Anyone knows what that is? Switching mode power supply. Heard of it?
So basically, I think it uses like a very fast switch. They're boost circuit and they're what's the other raises the voltage or lowers the voltage.
Yeah.
They use fast switches.
So you correct. So you sample the input very
Sorry for interrupting, but I was studying for
sure.
you know if there's any is there anything
I don't see no glasses at least.
sorry.
No problems. So indeed, the way switching mode power supplies work is think of like the following. I have energy coming in or voltage coming in, and I need to supply some certain amount of voltage on the output. So which is a DC voltage going into your devices. So what we do is we first take that AC signal, we convert it into DC conceptually, but then we sample it. But the rate at which we sample, okay, so think about like multiplying it by a square waveform whose duty cycle I can change. It's called pulse width modulation. Then by changing the width of the pulse, I can change the fraction of time I'm actually connecting the input to the output, very, very crudely, okay? So if I am 100% duty cycle, I'm transferring the entire energy. If I am 50%, I'm transferring half the energy, or therefore half the voltage. And then they put it into a feedback loop to control. So this is how sort of we make these. What happens is when you are sampling it, there's some 10, 20, 30 kilohertz clock, and that signal emits. So if you ever look at your sort of voltage on your the voltage signal on your electrical network, you would see this few tens of kilohertz type noise which is out there. So all these things exhibit different electrical characteristics, and one could make use of those. So the loads do not have to be simply in terms of the power, real power consumption. There could be other aspects. We'll see shortly, but there are in AC signals, there is another dimension, real power versus sort of apparent power it is called. Okay, so you can distinguish between the two because AC signal can be expressed in a two-dimensional space as a real number and as a real and imaginary component, and then again one can use that as well. So, but basic idea behind all of this is that there's some dimension in which the signals differ, and we can use it to disambiguate that. So the original approach was, like I said, changes in voltage and current were measured, some clustering was done, and sort of and then from you disambiguate. I think now the technologies have become a lot more advanced. They keep track of the state of the appliance. They bring to bear some pretty sophisticated machine learning algorithms, and also there's a workshop around this, which I'm going to skip the original algorithm. So one of the things which happened is that instead of thinking of appliances that's simply on-off, you can have appliances which have multiple states. So you begin to keep track of them. So multiple state type appliances can begin to be modeled. Particular things like fans and all, which have a small number of discrete states, or like a computer, maybe on at different levels, maybe in standby, hibernate. You can begin to model these things as state machines, and then try to infer from the signature as to which state you are in. And now you are trying to do it for multiple things simultaneously. So a lot of subsequent developments, more advanced algorithms. At this stage, for big loads, for a small number of big loads in a household, this kind of classification is happening. So what companies like O-Power have done is they have built up the models, and they do the automated classification. They characterize like refrigerators from different vendors and things like that. So these algorithms are even able to identify like you are running a 1980s refrigerator of this model, and then they may target an advertisement at you, time to upgrade your whatever refrigerator and stuff like that. The problem though is that these things are computationally expensive. So it's one thing to do it at the back end the way OPAR is doing, but these are not something that can just run on a small box at a home, for example, that easily. Training and sort of the computational load is one of the challenge, but the basic technology actually has lots of other uses also. So for example, another use of this technology is the following. So earlier on, recall I kind of referred to that you may get a lower price if you agree to let the utility company shut off your refrigerator. So they have these outlets where the utility company will control it and they will shut down your refrigerator or your AC system. But then people cheat. Your outlet is still there, still being turned on and off, except that your fridge is actually on a different outlet or AC is on a different outlet. But this kind of signature analysis can help detect that your fridge was still running. So this is called non-intrusive load verification. That is, was the load indeed shut off? So there are other benefits for the utility company to be able to do this thing. What are the dangers? I mean, this clearly is a privacy intrusive kind of a technology. So there are certainly concerns around that. The state there's some work which has shown that the same signature analysis, they can even identify the TV program that you were watching on your big screen TV. Okay, so there's enough data in these signatures to be able to make some pretty deeper inferences about it. Now, a little bit of digression out here, just to that the AC signals do differ in some ways, and which makes actually nylon problem easier in a way at some level. So for any electrical load, this basic physics, it is true that power is voltage time current. So I could always sample voltage, sample current through some sort of a digitizer, and then multiply the two, and I would have basically P of T. And then I can take the average and work with that. AC circuits or AC systems are bigger appliances, differ in that your voltage is sinusoidal. So that what comes out of the generator is some sort of a voltage multiplied by cosine of some term like this. And then most of our loads are assumed to be linear time invariant load, basically meaning that they're linear, they don't exhibit any harmonics and all, and the other thing is they don't change over time, or at least not sort of on a continuous basis. So under these conditions, it turns out that your current is also going to be sinusoidal, but with some phase lag. So if it's a resistive load, then voltage and current are going to overlap. That is, they will cross the zero at the same point in time. But if it is inductive load or capacitive load, then the current and the voltage are going to be in different phases. They're still going to be sine wave because we're making the linear time invariant assumption, but they're going to be separated out. And it turns out that many of our loads are capacitive. Capacitive is very rare, but many of our loads are inductive. Anything motorized, like fans or swimming pool equipment, these kind of things are inductive, and also laptops and these kind of loads are also inductive. So this gives us another possibility, which is we can begin to think of, if we can see this phase difference between the current and the voltage, then that can begin to help us disambiguate loads which may otherwise be similar. Now, this goes a little bit sort of deeper a little bit. So resistive loads, as I said, current and voltage are always in sync. So if I were to look at current and voltage, they always are identical, and therefore when I do power voltage time current, it is always going to be a positive number, and therefore there is a net transfer of energy that is I'm going to essentially consuming that much power. But let's say they were out of phase. Let's say what happens is that I had a capacitive load or a load which was pure capacitor or a pure inductor, then what would happen is that half the cycle the product will be positive, half the cycle power would be negative. You multiply them, you will and kind of integrate them over a cycle, you will get zero energy transfer. So capacitive or inductive load, there is no net power which is happening, but this, of course, what is really happening is during half the cycle, power flows from system to the load, the other half load back to the system. Sorry, from the appliance back to the grid. But utility companies obviously do care about this because there's still current flowing back and forth, and there are waste since they're supplying current, so there's going to be heat related losses and all, and wires have to be sized and things like that. So utility companies actually do care about the so-called reactive power. There's no net transfer of power, but I'm still kind of there's current which is going back and forth. So practical loads are a combination of these different kind of loads. So what happens is, so going back out here, in case of resistive load, I'm always positive. In case of an ideal capacitor, this thing, I'm half the time positive, half the time negative. So note that thing. In reality, your load may look something like this. That is some difference between the two. This relationship between how much of real power you are consuming versus how much of this fake power you are consuming is what characterizes a lot of these loads. And if you can measure that, then that's how we can begin to disambiguate things. So that's the phase between the current and the voltage. Or another way of saying is you're characterizing the nature of the load, how much of it is resistive versus capacitive or inductive. So what happens, and I'm going to skip these two slides, when you use one of these power measuring things, which are measuring power for AC, what you will see is sometimes they'll just give you a number which is the power number, and in that case it's the real power. This is what you pay dollars for. But a lot of these things will also give you what are called as reactive power, which is the component which is the imaginary dimension. So that sine wave you can express as a vector in this phase space, and then the magnitude of that is what is called as apparent power. So this apparent power is expressed in volt amperes, whereas real power is expressed in watts. So you would see, like some of the equipment, they will say 100 volt amp, then they are actually referring to this. If they say 100 watts, they are referring to this. Okay, and the ratio between the two basically is going to give you this phase angle. Okay, so and this, I think the cosine of this phase angle is called power factor. Okay, the upshot of all of this is that there is actually the second dimension that you can use. So two loads may otherwise look identical. They may have the same amount of real power, but their phi may differ, and therefore I can, if I look in this two-dimensional space, I may be able to distinguish them. So a lot of nylon systems make use of this capability also. It turns out, like for separate reasons, this power factor matters, because as power factor begins to be such that you have a lot of this imaginary component, then the utility company is doing work for you, but you're not paying for it. Okay, so they like to keep the cosine phi, the phi to be close to 0, so power factor of 1 is a good power factor. So if you have a home full of inductive loads, the utility company is going to not like it, because they are supplying current to you, and therefore they still have to size it, but they're not able to bill you for that. So what they do is, in some cases, they would, particularly for industrial organizations and all, they'll say power factor quality has to be maintained. So that's sort of digression. Coming back out here, for nylon, two systems transmitting the same amount of real power may have, therefore, different characteristics still. So the original nylon algorithm, Hart algorithm, they were just looking at real power numbers. So they were missing out on these additional sources of information that currently exists, and nylon could exploit this. So this is an example where what you see out here are loads whose signatures are now done in real power as well as reactive power. And what you see out here is, like for example, these two loads, the refrigerator and the water pump, they have the same amount of reactive power, but they differ in the real power. On the other hand, there may be loads like this IR light and garage door opener. They have roughly the same real power, but they are disambiguated in the reactive power. So the more dimensions you have in the data, obviously it can kind of help you. So that's sort of one strategy that NILM brings to bear, that look at this more complicated aspect of power consumption. This is another example, incandescent light bulb, computer, and again you would see that while in, I guess, real power they are identical, but in reactive power there is some separation, and one can sort of disambiguate using that. Now, there are even better things that one could do. So another aspect that NILM algorithms make use of is we started out by saying loads are linear, but loads are not necessarily linear. A lot of our loads are non-linear. So what that means is, if loads are non-linear, that means the current that sort of is drawn out of it, it not only has the 60 hertz component or the omega component, but it would also have higher frequencies, Fourier decomposition, so 2 omega, 3 omega, 4 omega. So there's also going to be energy in higher frequency components. So these are loads which draw distorted, non-sinusoidal currents, because that's how their underlying physics is. So what you could now do is you could do a Fourier decomposition. So look in the frequency dimension, and now you will see kind of essentially look at the spectrum and see where the energy consumption is, and again you can use them as additional sources of information. So like any machine learning problem, the issue is that yes, these things are separable. You have to find the right dimensions in which they are separable. You start out with, so the early NILM scheme was just looked at real power. Then you look at real and imaginary power, and then you kind of start going into these other, like the spectral coefficients, or perhaps other things, and even things like time of day, and all these things can begin to matter as well. So it turns out that now the NILM schemes actually can do some pretty amazing stuff, disambiguate kind of enough large number of loads in very subtle ways. So here these are showing things like where if you look at the third harmonic, then you can begin to disambiguate stuff. It turns out that there are other interesting uses of this kind of technology. So it turns out, like for example, when a motor begins to break down, some damage begins to happen, a crack happens or something, then these harmonics appear in the current it draws, and you can use them as an early detection of damage to a system or failure to a system. So there are other uses also, but NILM folks are exploiting this thing quite a bit. Now, additionally, you can do this classification at a snap point in time, but then like any machine learning algorithm, you can also do it as a trajectory over time. So for example, using sort of essentially take a set of measures, at every time step you kind of make a classification, but then you stitch them together into a trajectory. Like for example, using methods like hidden Markov model or conditional random fields. These are more advanced techniques where you can do even more powerful stuff. So what happened? So what has begun to happen now is that these problems are not simply treated as classification at a snap point in time, but classification over time, so that you look at a trajectory and then say, okay, this was a fridge, or this was a light bulb, or I guess someone made, like you had made the comment that the computer's load is going to differ, change over time in a different fashion. So you begin to make use of these kind of effects also. So lots of advances happening. Okay. So that's this central signature-based, throw machine learning at it, analytics at it, and there are several startups and public companies like Opower, which are kind of essentially running this stuff. This kind of technology is also applicable for gas, water. Same kind of concept applies. The University of Washington group I mentioned, one of the things that they showed was pretty cool. They put a pressure sensor, water pressure sensor, at someplace in your home's water network. Now it turns out every time you turn on a faucet, like kind of pipes vibrate and all the water pressure changes. It turns out every faucet in your home has a unique signature. So when you turn on the faucet at point A versus point B, there's a different signature pattern that emerges. And they train for that, and then they identify which faucet was on for how long in time. They do the same thing for gas. So it turns out when, let's say, your water heater uses gas versus your kitchen oven uses gas. So when the gas flows, there is essentially acoustic emission out of the gas carrying pipe. They pick that up, look at those signatures, and it turns out that different appliances have different signatures. So this ambiguate goes. So this concept of nylon, generally speaking, is basically saying that, look, indirect observations or these signatures can carry a lot of information, and if we throw analytics at it, one could do some amazing thing. Now, the problem with this kind of approach. So one problem with this kind of approach is that they tend to be good at giving us average power over kind of longer time duration. But if you're interested in very fine-grained power sampling and all, they do not. They do not do that. The other part is they require a lot of training. So in the absence of that, they're sort of able to give some general guidance, but not very accurately. So there's a middle class of techniques also which sort of emerged, which sort of take a intermediate approach, which essentially works by making use of various kind of side channel signals. So kind of the idea out here is the following. Let's sort of combine the benefits of the two. At the appliance level, if we can get some sense of whether the appliance was on, off, or how much, whether it was consuming high energy, low energy, some indirect signal that we can make use of, and then we combine it with a reading at the meter. So the way it kind of works is the following. So let's imagine, okay, let me stick with the previous slide. So let's imagine the fridge or the electrical wire, I place a magnetic sensor, light sensor. So I'm getting information about the state of these appliances. I'm not actually getting information about how much power they're consuming, but I'm getting some information about the state. Like, for example, change in magnetic field may say something about an appliance going on, or in a light sensor in a fridge can tell me the fridge door was open, or perhaps a vibration sensor can tell me that the compressor fired up. I could combine these things together with the following observation, that whatever my meter is saying is the current power consumption must add up to what my models are saying for each appliance. So I do not know, I have cheap sensors telling me something indirect about the appliances, but they should add up to the overall power consumption. This is something that we saw policy 5 in the paper that Fatma presented last time, that for a computing system, again, we have the same thing, which is total power consumed by the computer must add up to what the individual principles were consuming, okay, and that should hold true for at any point in time. I do not know what individual principles, I only have a model for it, and that model may or may not be accurate, but what should hold true is that the summation of what I'm claiming for individual appliances must add up to what my meter is saying, okay, and these models could be learned. So you could imagine like the following. Let's say I start out by saying that each appliance has a very simple model. It consumes some constant plus some second constant time what my sensor is saying. Okay, so it could be appliances which have a constant component and a component which is linear with something that I'm sensing, linear with the airflow, or linear with the amount of sound they are making. So let's just start with something like this. But you can imagine other types of models also. So then essentially what we have is a model learning problem. I'm starting out with models for each one of the appliances. I do not know those parameters, but over time I'm making many observations. Okay, so I'm getting different meter readings. This would correspond to, again, taking the analogy with that paper, different subsets of appliances being on at different times. So I'm getting samples of overall power consumption under different settings of what my sensors are reporting, and then over time I learn these alpha and beta parameters, and again making sure at all times my models add up to this. So I could put these sensors in this kind of a feedback learning loop, making use of this thing that main meter should always add up to the individual meter. So this kind of technique is called virtual metering, but essentially I'm using one high quality sensor, namely the meter, lots of cheap indicators of things being on and off, and then calibrating them and continuously kind of correcting them. So sort of do some model-based power consumption and do the recalibration. So this virtual metering approach has been applied in many different settings. Again, water, electricity works pretty well. So this is an example where this is the ground truth. This is how what the measurement was reported, and sort of you could see most of the nuances are being captured. Same kind of thing has been done for computers also now. So in case of computers, the visible things are what your OS can tell you, how many cycles, network packets, stuff like that. And you again have a model where you basically say power consumption is a linear function of some of these things. You add them up, make multiple observations, learn them. Okay, the same kind of concept. What I have not seen is the Shapley type economic model being applied to buildings, but one could imagine the same thing being done for buildings, and perhaps giving better. One nice thing about buildings as opposed to computers is that ground truth is easier to get because you can always use direct sensors with appliances and all and collect the ground truth. So how well you are doing, you can actually measure. So this is from that example I've shown, and you'll see that a couple of percentage point type errors, which is pretty good. Not meter quality good, but good enough for making kind of seeking to change behavioral patterns of individuals. So same concepts for water metering. Again, you can have direct, indirect kind of approach. This is the work out of University of Washington I was describing. So they basically put a single pressure sensor at one of the garden hose faucets, and based upon the transients in the water pressure, they disaggregate water consumption. And similar concept, I think. Yes, this is called HydroSense. I'm going to skip this. So these are the kind of signals they see. How the water pressure transients happen when the faucet is opened, stabilize pressure, the faucet is closed. So signatures, bottom line, signatures can do a lot in all these different kind of things. So for water. Another one, this was actually work here at UCLA. This was for side channel monitoring for water pipes, and I want to show again how machine learning kind of techniques can help quite a bit. So in this case, again, we want to identify how much was the water consumption out of an individual device, and the side channel signal that is being made use out here is that pipes vibrate. So when you use water faucet, they vibrate, and it turns out that the vibration follows the water flow according to some reasonably nicely behaved cubic function, which looks like this. So I have a model now which basically says vibrations, which I can very easily sense, flow, which I cannot sense directly easily, are related by this equation where I have some parameters, alpha, beta, gamma, delta. And I again use the same idea that we had previously, which is I have an accurate central meter. I have a bunch of these faucets, each one of them with their own alpha, beta, gamma parameters. Over time, I take multiple readings and I learn these parameters for the different faucets, and then eventually kind of converge. So essentially, you have a self-calibrating system where you're learning these parameters. So same concept. What you're metering should equal to what your models are predicting, and then what with that. There are some additional effects that you have to take into account. So like in case of water system, when I turn one faucet on, there is also going to be vibrations at other faucets. So there are some cross effects one need to take into account, but similar aspect kicks in. let me just jump to the end result. Skip the math. So in this case, what you're seeing is estimated true pipe, true water flow. Again, you see kind of the transients and all are getting captured. So these kind of modeling techniques are pretty powerful, and they eliminate the need for costly sensors everywhere. So 2-month deployment in a home, and again, turns out to be pretty highly accurate. Gas metering, same concept. So at this stage, this is out of University of Washington, where they use a microphone next to the gas meter. They pick up an acoustic signal and apply this concept out there. So they, in this particular case, the signature they look at is in the spectral domain. Okay, so yeah, so this is the example from their gas system where they're able to detect how much gas is being used by water heater versus stove versus fireplace by, again, this kind of a signature analysis. So upshot is that at this stage, sensing technologies are pretty good, at least for the purposes of conducting the kind of studies and all after. They're not cheap to be able to widely deploy, but relatively non-intrusively or easy to deploy fashion, particularly these things which work purely from meter data, they can make a lot of inferences. So next what? So what's now begun to happen is people have begun to apply these things to control stuff. And main thing driving this stuff is the fact that there are variations in the workload and there are variations in the energy availability. In particular, when it comes to electricity, we have time of use, peak load. Same kind of thing is happening in water, gas not so, but water and electricity are both being affected by that. Their availability varies, and therefore the price varies. When you use the water or when you use electricity, the cost it takes to supply varies. So what has begun to happen now is use these sensing technologies not simply to change behavior, but to also seek to automatically control loads in the building, for example. So one area which has received a lot of attention is occupancy-based load management. So kind of concept basically is the following, that could I make a building more energy proportional or more energy proportional for the most part by shutting things down in a smarter fashion so that as occupancy changes, the load and the load offered by the building changes. So reliable sensing of occupancy is a very important aspect. So let's look at this room. The simplest model is there's perhaps some sensor in this room which detects is there someone in this room, and then adjust things accordingly. So light probably has to be on, but let's look at the airflow. If there's one person in the room versus, I don't know, roughly a dozen of us, the airflow can be changed because there is standards in terms of how much airflow per person should be there, because as we are in this enclosed room, we are breathing, carbon dioxide that comes out, that needs to be removed. So the amount of airflow that, or how much air has to circulate through this room is a function of how much occupancy is there. So buildings started out with the model that they had no idea of occupancy, to one where now they have some idea of occupancy. So currently this room has no idea of occupancy. So airflow is held constant. Lights are on. Lights, probably there's a motion sensor, so that can go off, but the airflow is sort of constant. So what's begun to change now is that could we have more precise estimates of occupancy, and then change what is happening. Okay. So that's another direction that sensing is taking. Is a room occupied or not? How many people are in the room? What activity they are doing? So like, for example, if the activity is relatively sedentary, then the airflow can be less. If on the other hand, activity is something which is burning, which is affecting the air quality or requires additional airflow, then you indicate that. What locations are individuals in a room zone? So for example, if you look at this room, there are perhaps 3 or 4 of these outlets. which one airflow coming down, which one of them should be on, can be impacted by where the individuals are in the room. What are their identities? So perhaps different comfort levels which are needed. So all of these things come up in a shared space where many individuals kind of exist. Problem though is that the occupancy knowledge currently tends to be either absent or basically is there someone in the room, and not so much on how many people are in the room. So since all of you have been quiet and I've been speaking, so let's think about how can you measure how many people are in a room.
Maintaining the counter, how many people enter, or how many people exit.
Okay, and how might, so some sort of a sensor at the door, which I don't know what kind of sensor.
VIR.
VIR. How would that help?
It has an infrared, and it will measure if somebody has lost by the sensor.
Okay, so okay, so possibly. Okay. Any other ideas? How can you sense occupancy, or how people are distributed in this building? Let's say.
I think its accuracy will not be high if you like measure the temperature with oxygen in the place. I think you can get some.
Yeah, actually, so you measure carbon dioxide level. Okay, so one thing that these AC systems do is, as the air is flowing, right? So there's air coming out, and then I guess some of these are probably back. The air goes back. So the air which is going back has a higher concentration of carbon dioxide, and therefore somewhere a carbon dioxide sensor can sense it. Okay, but accuracy is not very high because.
People change it.
Huh? Well, it's a long time constant process, unfortunately. So that's one of the issues. It takes long time. Okay, so it's not going to reflect immediately. But yeah, it could. In fact, that's the technology that sort of is widely used. At a central point, they can kind of get a sense of how many people are in a building. Okay, and they can change the airflow accordingly. They are not able to kind of identify how many people are in this room, and all that level is not there, but certainly over a larger space. Anthony.
What if you had like infrared like heat vision camera
Okay.
in the room,
So
you can see heat signatures?
yeah. So
Microfiltering stuff.
so people are using it in some pretty creative ways. There's some work out of University of Waterloo, I think it is. What they even do is they seek those heat cameras to identify where people are, where are they working in the kitchen, are they using the microwave, are they using, okay, and then they make use of that in some creative kind of way. So certainly you could. Jeremy?
Electrical signals from a cell phone or some device or something?
Yeah, so that could be, I mean, our devices emit stuff, or I mean, they could localize my laptop, and then so with the signals that the access points are getting, so network traffic, phone traffic, those kind of things can certainly be used, and all of these things can be brought together. So I've seen some work out of IBM and all, where they have actually kind of deployed a collection of these technologies together to really begin to say something about occupancy patterns at a much finer way. There are a lot of other signals like usage of telephone, okay, in office buildings and all, since they all connect to a PBX, so that's easily keyboard activity on your desktop computer, those kind of things can be done. Obviously, cameras, I mean, that's another possibility, although sort of more intrusive. So, coupled, so when it comes to this load management, there are many things. The one obvious one is the uses of the appliances themselves, right? I mean, if the projector is being used, then say something about occupancy in this room. When we go around our home, we turn on lights, we use appliances. So there are obviously these signatures which are kind of also present. So so lots of sources of information which are out there. The occupancy patterns tend to be pretty diverse. They depend upon what kind of room or building it is. So a lot of the work which has been happening in recent times is looking at how could we make use of occupancy to manage the energy load. Now there's simple stuff like space is occupied versus not, you turn on and off things. But you can actually do a lot more creative stuff like based upon anticipated occupancy, you can begin to do things. So let's say, for example, let's say now, during this part of the day, this room, other than our lecture, nothing else was going to take place. So one strategy would be when we leave the room, then the airflow is shut off. Or, okay, but you could also imagine strategies that we know the class is going to end at, I don't know, in 6 minutes. So it could begin to shut off the airflow prior to that, or begin to increase the temperature prior to that. So this kind of a I guess the analogy would be when we talked about the shutdown of CPUs and all, the analogy out here would be that we can pre-wake up or or shut down in anticipatory fashion. So these kind of techniques can also be used pretty interesting. So occupancy information can be used in a planning stage, could be used in a reactive way, or could be used in a predictive way. So lots of work which are happening, and kind of couples back to this demand response type thing, which is when energy prices change and all, could we basically control the systems in a building in a smarter fashion. So in that case, it is being driven by cost, but cost, comfort, all those kind of things come into play. So the way things happen in demand response is that now driving all of this is that there is some sort of equipment in the building which is receiving pricing signals, or currently what happens is there are pricing websites from which utility publishes the pricing data. Your building is going to fetch the data, and based upon that is going to modulate its behavior. Loads which are shiftable will be shifted. Parts of the building which are expected to be not used, or based upon this finer grained information of occupancy, smarter control can be done. Okay, so there are appliances and all which are emerging now, which are called demand response compliant. So what they usually have is that embedded in these things are essentially little controllers. They usually speak Zigbee, same radio standard which are very commonplace in sensing and all also. And then the idea is that at runtime, their behavior is controlled based upon what is happening at the building level. So there are, on the market now, there are fridges, washing machines, things like that, which based upon the signal which the utility company is providing, can delay their cycle. In case of fridge, what may happen is it may cool it more and then lower the duty cycle of the compressor at when the energy price goes high. Yeah, dishwasher and other sort of things.
So the Energy Star, that talks to the energy company, but
it actually talks to your meter. So what happens is the meter is kind of like the gateway. It has a Zigbee. So modern electric meters, they actually have a little socket, which name I forget, but it's essentially a standard socket for communication interfaces that the industry has agreed upon. So there are Wi-Fi radio modules and all, but the common one which is used is Zigbee. So meters come equipped with that. These things that I was showing, they are all equipped with Zigbee, and essentially your meter commands the appliances. Okay, and then it can verify, so chooses via the nylon type of techniques and all. Okay. So there is Professor Rajat Garg's lab in E4. They actually have a whole pretty cool kind of showcase system built around these kind of refrigerators, and also his whole lab, which is maybe 2 times the size of this room, is equipped with a lot of these kind of appliances and all, which all talk to a demand response system and are managed automatically. So some pretty cool stuff going on around this. On a more residential level and all, currently, I mean, if you don't have those kind of appliances and all which come built in with this, there are a lot of products like these which are controllable, and one could sort of subject them to the same kind of strategies also. Yeah, this is, so GE has a lot of stuff I kind of already showed on this thing, meter to appliance, home, and there are a lot of companies which are selling kind of these kind of devices and all, also gateways. One sort of company, so Nest thermostat, I'm sure many of you heard about it. It also actually has the similar capability apparently, but they have not activated it. Okay, so it senses and all, but it actually also have the ability to sort of talk back to these appliances. So gradually we are seeing penetration of these kind of technologies, but the basic idea behind all of them is that eventually our homes will respond in some pretty flexible or proportional ways to the energy pricing, and you can have these kind of different strategies of like doing things in advance, shifting workloads. The washing machine can detect that there is no load being done, or maybe instead of just turning on the machine, when you turn it on, it will give you an option of just delaying things for the future, so that there is more sort of control. So, and the final bit, which I already mentioned earlier, is the ability to actually verify the response. Okay, so that's pretty important because all these pricing strategies and all open up the possibility of cheating. And so for utility to be able to verify what is happening, that you actually shed the load or you actually responded to that demand response signal. And what is happening is the same NILM techniques are being brought to bear out here. So I'm going to skip that part, but the basic idea is it's the same non-intrusive system which is done, except that in this case, it is being used to verify that a particular load was shut down as opposed to doing disaggregation. It's a easier problem in a way because you are focused on a specific appliance and you are seeking it being on and off, as opposed to an arbitrary, like essentially an arbitrary disaggregation problem. So people are, I guess, more recent work that I've seen this year, what's happening is they're marrying more detailed physical models of appliances and all with more general machine learning techniques to create more powerful ways of doing this stuff. And same ideas are filtering back into disaggregation of like what is happening inside a chip or inside. So it's very hard to instrument subsystems inside a computer because sensors on chip or sensors on the board add to cost, and also same concepts of non-intrusive stuff basically are getting applied there as well. Let's see. Yeah, so I'm going to stop